about a way in which you can describe abstractly the protocol by which two separate threads access the same state, and then make sure that those protocols work together safely to avoid interference. This is joint work with my student Philippe Militao and his co-advisor Luis Kirsch. I'm sorry that Philippe can't be here. This is his thesis work, but I'll do my best to do it justice. So our work is motivated in some sense by API protocols. Many libraries define protocols that show how you should interact with them. A protocol is some abstraction of an object state space as a finite number of abstract states that clients have to know about in order to use that object correctly. So here's a stream example. We have open and closed states, and we can have read in the open state, but not in the closed state. And then there are methods that transition between these states as well. And we can look at it as a state diagram, or we can also look at it as pre and post conditions for the various methods. So read has open as the precondition, leaves the object in the open state, whereas close will transition the state of the object. Now, as I said, clients have to understand and follow these object protocols. But unfortunately, we've seen that, especially in examples that are more complex than streams, developers can have quite a bit of problems following these correctly. So Josh Sunshine, who is here at eCoop, has done a number of studies, qualitative studies, demonstrating that this is a real problem. And we want to find both to help developers avoid errors working with libraries that have protocols, and also increase their productivity. And we have some studies that show both of those things are possible. What I'll show you today is a theory that explains how we can do checking in furtherance of these goals. So this is part of a longer-term initiative exploring what we call type-state-oriented programming, also mentioned in an earlier paper here at eCoop, as a way of expressing and enforcing more aspects of design in software. So let me speak specifically to the case of concurrency and protocols used in concurrent systems. Some objects might be shared by clients that are in different threads, but if we don't control the way they access that shared state, there may be unsafe interference. And so we want to make sure that protocols of different clients compose in a safe way. Let me give you a very simple example. The paper has some more interesting ones, but this will explain the basic ideas. We want to have a thread that we fork off, and we want to join on it. And let's assume that our library doesn't build in join. How can we build this out of shared state? So we have a fork thread protocol here. There's going to be an object that is initially in the wait state, and when the fork thread is done, it's going to transition the object into the result state as a signal to the main thread. And as it does this, conceptually, we want to give the ownership of this signaling object to main, so that main can then read the result out of the field. On the other hand, the main thread protocol has to test the state. And so what it's going to do is it's going to lock the object and look at its state. If it's still in the state wait, then we just have to loop back and keep testing. But if we find out that the object is in the state result, then we can go and read the state, and the protocol completes. Okay, so this is a fairly simple protocol, but you can imagine there are a number of ways to go wrong. Here are three possible ways. We could manipulate, in the forked thread, we could manipulate the join data structure further after making this transition instead of giving up ownership. Okay, so that would then cause a problem where we might be writing to this as the main thread is reading from the result. We could transition to something other than result, which would be unexpected to main and cause main to have an error or to perhaps wait forever. Main thread could maybe not wait when it's supposed to. It could read early, and then that read could race with the write in the forked thread. So there are a number of things that could go wrong if these protocols don't actually match up. So we're doing this in the context, of course, of a lot of prior work on type state checking systems and safe systems for concurrency. This includes our own prior work on object-oriented type state, as well as others like a founding work by Fendrick and DeLine. But the type state systems in previous work didn't really look at separate protocols for separate clients. They really only looked at an object as having one protocol, typically. And furthermore, they weren't very abstract. They were often, they had the state of the object, but then also some abstraction of its permission, right? This object is unique. So because of these things, we weren't able to express our examples, and kind of more of the machinery was exposed than we really would like. So we'd like to address both of these systems in the context of type state. There's other work on session types and separation logic that I could discuss as well. Session types actually have this characteristic of viewing shared state from a multi-party perspective, but they are more focused on message-driven computation, and that's very good for modeling actors and distributed communication. But we want to really link more closely to state changes. Separation logic is also very expressive, but typically you give up a guarantee of decidability that you get from type systems, and we want to stay in that world. So I'll say more about that. It's a major result of our paper. So what do? We extend the idea of rely guarantee protocols from ECOOP 2014, Philippe's paper there, and we prove an absence of concurrent interference. And this is an extension to the concurrency case. So before we were looking at shared state, but shared within one thread. So this is a foundational calculus, but hopefully it can be built into practical language designs in the future. One key thing we looked at was how to provide protocol abstraction. So we want to view a protocol as an abstract state that hides the internal details of the object and helps to decouple protocols, and also allows after-the-fact specialization. So I'll show how you can actually nest one protocol within another due to this notion of abstractness that we can support. That abstractness actually makes reasoning about the protocol more difficult, and I'll explain why and how we address that challenge. And then finally, some validation, both in terms of type safety and a number of examples that talk about the expressiveness of the system. Okay, so first of all, how does the system work? Let's dig into this thread join example in a little more detail. Here we have the main thread. The main thread is going to create a cell, and it'll be in the initial state wait. It'll mark it that way. And then we'll create this forked thread and pass a reference to the shared cell. Now, when we do that, we need to specify what are the protocols by which the main thread and the forked thread will access this shared state. So we'll say there are two protocols here. I'll call them M for main and F for forked. And forked thread will have the F protocol permission, and we'll have the M protocol permission up there in main. So now let's see what happens when the threads do different actions. So let's say main takes an action first. It synchronizes on the object and discovers after testing that it's in the state wait. Okay, so the protocol says we have to leave the object in state wait. So this is a transition. In this case, the transition just leaves the object where it is. And we continue with the protocol M. Okay, so this is just a way of looping back to the beginning of the protocol. On the other hand, and we could do that as many times as we want, at some point the forked thread will finish its computation. It will synchronize on the object. The protocol guarantees that the cell is in state wait, so we don't even have to test for that. We'll assign into that cell, so it changes state to the result state. And we'll store the result, any result of computation we want to pass in. We're modeling it as an integer here, which I'll show in the next slide. And the forked thread then continues with the none protocol. What does the none protocol mean? It basically means the forked thread won't access the cell anymore. So that's a way of saying that it gives up ownership. Now, of course, if the main thread comes back, it'll synchronize on the cell, discover that it's in state result, and it can go and read the contents of the cell. Just for explaining how things work here, the read is actually destructive in our formalism. You wouldn't necessarily have to implement it that way, but in our formalism, the cell is left in a different state because of this destructive read, which we'll call done. Again, there's a state transition from result to done. The main thread continues with the protocol done, and there's no transitions there, right? It's just I have an object in state done, and that actually means that main now owns the cell and it can do whatever it wants with it. Okay, so that's the basic idea of these protocols. And we call them rely guarantee protocols because they're these protocols that involve transitions, and so you can always rely on the object being in one of the states on the left, and then you have to guarantee that it's in the state of the right when you let go of it after every transition in the protocol. All right, let's push forward and look at spawning a thread here. What does the code look like? So here we have a spawn procedure, and we're just going to create this cell, and it's initially in the state wait. Wait in the previous diagram was actually an abbreviation for something a little more detailed in the calculus. This just says I have a permission, read-write permission to cell C in the wait state, and the cell is holding just something empty, right? Unit. So now we'll split this protocol into the states, the protocols M and F, and the child gets the F protocol when we fork. We do some work in the child, we get an integer out of it for R. When we lock C, then we go into the F protocol and we discover, oh, this must be in wait, because that's what the protocol says. And so in this critical section, we then can assign to this resource. So this assignment wouldn't work unless we actually had a permission to that cell, but it does work. So we assign to it, we tag it with result R, with the tag result, and we pass in the integer R. Now notice that the type we have for the cell matches the type that we need to establish at the end of the critical section. So that was what it was on the right-hand side of the arrow in the protocol. That arrow describes what the critical section does. It goes from wait to result. So now that we've gotten where we need to be, we can go and unlock. And then after the unlock, we have left nothing, right? The fork thread now has to be done with this cell. Okay, so I could show you similar code for main, but we need to get on to some of the other interesting bits of the research. So let me push forward, hopefully with this intuition. But that's the first contribution, is really taking the idea of rely guarantee, which we presented before, but pushing it into the concurrent setting in type state. Obviously, rely guarantee comes from concurrency, and there's a long train of work on that. But for logics generally, rather than for type state. So now this is a protocol, and the idea of it is abstract, but if you look at the details now that I've shown you them all, there's some complications, right? I've showed you, well, wait is really, holding some empty data, result is holding an int. We can make this more abstract. For example, we don't need to say what wait has inside of it. We're not actually even using that. But if we make wait parametric, that's actually better. Not only is it more abstract, it's more flexible. We can then later nest another protocol inside this wait protocol. Okay, so let me use polymorphism. Instead of having a protocol F, I'm going to have protocol F of X. So for all types X, or all protocols X, then we could have wait, store some permission to that X protocol, and then F just says we transition to result. But notice that kind of for free, since in this protocol the fork thread really owns the cell, we can also transition from weight of X to weight of any other thing Y. So there's a universal quantifier here. For all Y, we can go from weight of X to weight of Y. And this is going to let us actually nest some other protocol inside. So let's say that inside this fork thread, we actually want to fork again and do some work by the children and then combine them. So we could have a protocol for that. I'm not going to show it, but there's an example in the paper. I'll call it K. And so we could actually split f of x into K parallel with K. And we could keep doing this if we want. So this abstraction actually, it hides some of the internal details of what are in these states, like it abstracts what's inside wait, and then we can do interesting things with it and compose one protocol within another in a very nice way. Okay, so this is the second contribution of the paper. Now, protocol, actually checking this is kind of interesting. We have to make sure that, when we start with this wait cell that we created, it's actually safe to split it up between these threads M and F, between these two protocols M and F in different threads. So how are we going to do that? Essentially, we want to model check this state space. So we're going to start with an initial state, wait. That's what we started with, and we're going to execute protocols M and F in parallel abstractly, and make sure we don't ever get into trouble. We would get into trouble if we got into a state where one or both of the protocols couldn't do anything. Basically, we would be stuck. So we don't want to get stuck. Let's see how we do this. In this example, here's our initial state. Here's our protocol that I showed you before, and we'll take we'll look at the transitions one at a time. So the main thread could take a step, but wait just transitions to wait and goes back to protocol M. So this is just a self loop. We could also take the transition of F, so this is here the wait turns into result, so we'll go into result, and our F protocol moves into the none state. That's what's left after this transition. And so F goes to none down here, and the state of the object goes from wait to result. Now we can look at this other transition from result to done. It's the main thread's transition. And so we go from result to done, and the protocol goes from M to what's left after this transition, which is done. For technical reasons, we can step from done to nothing. That just means the thread kind of takes ownership of this and maybe deletes it if it doesn't need it anymore. And none can take a step to itself. So we now have a complete state transition diagram, and notice that we've actually explored all of the possible states that we're in, and every state has some transition going out of it, including technically this last state that can just loop. And so we don't ever get stuck, and that's kind of the theme of the paper, right? Milner said well-typed programs don't get stuck, well-typed protocols don't get stuck either. So that's the basic idea of checking. It gets a little more interesting when we check in the presence of abstraction. So remember I showed you how you could generalize this protocol of wait and result with where we don't necessarily know what's inside the cell when it's in the waiting state, and in fact allowing transitions from one thing to another. Maybe we store floating point numbers there for a while, and then when we transition to result, we put an integer in. Okay, so that would be possible to express in our system. So here is that expanded protocol. We have f of x, and we have wait of x here. I've abbreviated wait with w to make the formulas a little shorter. And here we have, we say, well, I'm going to transition for all y into some state y. So I have to expand the procedure I showed you in the last slide just a little bit to account for these type variables, or these protocol variables. And so we start with the state where the cell is in state wait. And it's in wait of x, so we know x is just some type. Type describes protocols as well as cells in our formalism. And we have to step it. So let's step it according to this state transition. Well, we're going to some state y, so we actually need to add a y to our context. And our cell is now in state y. But y could be an x in general, and so we could take this state transition again and go into some other state z. And now it looks like we're in trouble, right? Because these states all look different. They certainly have different contexts. The context gets bigger with each step, and we might never finish model checking the system, right? We want to fully explore the state transitions, but it looks like there's an infinite number of states. But of course, if you look closely, what's happening on the right-hand side, well, it all kind of looks the same, right? It's just that there are different variables being generated on every route through the cycle. So it turns out that we can use weakening and alpha renaming to show that these extended contexts are actually equivalent, even though we're denoting them in a different way. And so the paper has a description of the reasoning in more detail, and Philippe's thesis has the complete proof that shows that actually for every protocol you can express in our system, you can finish type checking it, right? You won't get an infinite set of states like this. Type checking might fail, but it won't ever loop. So that's how we get a decidability result, which is the third contribution, right? Figuring out how to check these things in a decidable way, despite the fact that we have abstractions and type variables that get generated and so on. So there's more in the paper. There are theorems for memory safety, race freedom, and decidability of the checking system. We have prototype implementations of the protocol composition, as well as the base language. This is actually without concurrency. This is from the previous eCoop version. But the protocol composition is kind of the tricky new bits, and so we implemented that again. You can try it in a browser if you want to try it out. But I also encourage you to look at the paper. We have a nice example of message passing concurrency that's expressed through this system. Some other idioms like hand-over-hand locking and mvers and so on. So it's actually pretty expressive. Okay, so I've told you about how we can define a type system that links the state of an object to different concurrent protocols that safely coordinate to access the shared state. We have safety and decidability results for the checker, and we have the new bit here is, as well as the decidability, is abstraction that allows us both to hide the representation and kind of specialize and extend these protocols in very flexible ways. And then also some expressiveness, which I wasn't able to say a whole lot about, but hopefully you can have a look on your own. So that's all, and I'm happy to take questions.
Thank you, Jonathan. You said that the three versions of the polymorphic protocol were equivalent, and you said how you could prove them, but I was not clear what they meant. To me, they look very much the same since the first use of F or the first appearance in what is happening. It says read, write, P, W, and then X or Y or Z. And in all of them are variables, and I suppose that the X does not appear again if we are in the second line.
That's right, and that's exactly the intuition for why we're able to do this, right? So it's possible that in a more complex system, there could be some relationship between X and Y. You could have a constraint that they were subtypes or something, and then it might be harder to eliminate them in this fashion. But we are able to eliminate them because you can never, because of the way we have specified our system, you can never have an unbounded number of types actually mentioned on the right-hand side. So you can always eliminate the ones that are not mentioned.
Right, so I think my question is, how do you prove it? Do you prove it by looking at the semantic of the thing, or do you do you prove it proof theoretically by proving that whatever properties one has, the other one has too, in terms of what you can prove about it?
I believe it's a semantic argument, but the way it's actually a counting argument in terms of the state space of protocol checking. So Philippe basically figured out how you can limit the number of steps that occur in an algorithmic version of this checker, and showed that at some point this doesn't keep getting larger, and so you can bound the size of this, and therefore you can also bound the total exploration, because this side the steps on the right don't actually get bigger.
So with the abstraction that allows you to change X to Y, you get a lot of freedom, but does that include the nested change such that you can change W hash X to W hash Y hash Z? Is that a built-in property of the meaning of your quantifier?
So the hash means tag. So W is the tag, and then X is something inside. But the something inside actually could be a tag value itself. Okay. And so, yes, indeed, you can tag the thing inside according to some separate protocol. And if you look at the definition of the sub-protocol that I hinted at in the slides, if you look at it in the paper, it actually does that.
So it looks like you have really nice fine-grained control over the kind of protocols that you can express. So are you aware of what are the limitations? Are there any kinds of protocols that are hard to express?
Yes. So fundamentally, we want to be decidable, and so the state space okay. So there's no limits on what Y and Z could be, but we're not actually reasoning concretely about them. So the things you reason concretely about, there have to be a finite number of them. So we actually have there's actually a sketch of how you would do a counter example in the paper, but it would require dependent types, that's one thing we don't have in our theory. There's the sketched extension, as I mentioned, but so any kind of infinite reasoning, numerical reasoning, that would have to be an extension, and you would have to make a separate argument for decidability if you cared about that.
I was wondering if you could extend this to a probabilistic setting where machines might fail, transition to a failure state, and then it would be, well-thick programs don't fail up to a given probability.
Yes, that's a great question. We have not explored that at all. I think it might be possible to leverage some of the same ideas, but it would be an extension.